Hello to everyone. In this video we are going to be solving a problem which is exercise 4 of an examination of the Harvard University, guys. So the question was proposed to me and I'm going to solve a series of equations, but we are going to begin with exercise 4. So the question reads, it is divided into two parts. Here is the first part. Find the eigenvalues and eigenvectors of the matrix A having entries -5, 2, 2, -2. The second part of the equation, consider the integral I to be the integral, that is a double integral in a domain D, of y squared dx dy, where D is a domain enclosed by the circle centered at the origin and of radius 2. The first part of the first question for the second part is represent graphically the domain. The second, determine the Jacobian associated to the change of variable from the xy wall to the r theta wall such that x is equal to r cos theta and y is equal to r sin theta. And thirdly, evaluate I, which is the original integral, using that change of variable that you have gotten in the second part of the equation. So pay kind attention to the solution of this problem. Alright, so let's begin with the solution of the first part of the exercise 4, which is asking us to determine the eigenvalues and the eigenvectors of the matrix A. So let's begin by determining the eigenvalues of the matrix, because for us to get the eigenvectors we need the eigenvalues, but to get the eigenvalues you just need its simple mathematical definition. So if lambda is the eigenvalue of my matrix A, then it follows the mathematical definition that the determinant of A minus lambda I is equal to 0, where I is the identity matrix, A is the matrix in equation, and lambda is the eigenvalue. So let's start by looking for A minus lambda I. It is simply the matrix A minus lambda times the matrix I. Since we are in the order of my matrix A is 2 by 2, then the identity matrix here is going to be the identity matrix in the 2 by 2 wall. So here's my matrix A, then minus my lambda times my identity matrix. So simply we can simplify this as A minus lambda I to be -5 minus lambda, because these zeros and zeros are still going to remain, but the lambda is going to multiply with 1 to give us lambda, multiply with 1 to give us lambda. Now subtracting two matrices which have the same order, we just subtract their corresponding entries. So here for the first entry of my matrix A minus lambda I is going to be -5 minus lambda. This entry is going to be 2 minus 0 lambda, but 0 lambda is 0, so we have 2 minus 0, and so on and so forth. We get this entry and this entry. So from there, the determinant of my matrix A minus lambda I is simply the determinant of this matrix. And how do you get the determinant of a 2 by 2 matrix? The product of the elements in the leading diagonal minus the product of the elements in the non-leading diagonal. Now the elements in the leading diagonal, you have -5 minus lambda and -2 minus lambda. We can actually factor the negative sign out here to get -5 into 5 plus lambda. Here as well, negative into 2 plus lambda. When they multiply, it becomes positive. So we get 5 plus lambda times 2 plus lambda minus 2 times 2, and 2 times 2 is 4. So if we expand this, we get lambda squared plus 7 lambda plus 10, then minus 4. But 10 and 4 are like them, so we can subtract them together and we get the determinant of that matrix in function of lambda to be lambda squared plus 7 lambda plus 6. But now we are to determine the eigenvalues, which means that we are to solve the equation, the determinant of A minus lambda I to be equal to 0. So that equating this determinant to 0, that is this equal to 0, means its determinant is equal to 0, because this is the equivalent expression of the determinant. From there you can factor out this expression on your left hand side, which is a quadratic expression. Factoring it out, you can factor out into lambda plus 6 times lambda plus 1 and equate to 0. So it means that either lambda plus 6 is 0 or lambda plus 1 is 0. So lambda is equal to -1 and lambda is equal to -2. So we have gotten two eigenvalues of the matrix A. Now we can use these eigenvalues to get the eigenvectors. So nextly, we should determine these eigenvectors. Now, to determine the eigenvectors, we're actually going to use each of these eigenvalues to determine the eigenvectors, because an eigenvector is associated to a particular eigenvalue. So let's begin maybe by letting lambda 0 to be -1. That is, we begin with our first eigenvalue. We call it lambda 0, and its eigenvector is the vector u0. Now, since we are in 2 dimensions, all our matrices are 2 by 2, then my u is going to be of the form x0 y0. So you have the u vector to be represented in this way. That is a row form of the vector. Alright, so from there, what is the definition of u being an eigenvector whose eigenvalue is lambda? It simply means that a minus lambda 0I, I've specified lambda 0 because I am dealing with a specific eigenvalue, times my eigenvector u0 to be equal to the 0 vector. So this is a mathematical definition. You just need to come and take the original times the eigenvector and equate it to the 0 vector. Remember, it is not equated to 0, it is equated to the 0 vector. Now, what is a 0 vector? Since we are in 2 dimensions, the order of our matrix is 2, then the 0 vector is just going to be 0 0. If we're in 3 if the order of all our matrices were of our main matrix A was 3 by 3, then the 0 vector is going to be 0 0 0, the column 0 0 0. Alright, so here let's determine this value, that is a minus lambda 0I. We know a minus lambda, it is this. So a minus lambda 0, we just replace lambda here with its equivalent value as -1, since that is lambda 0. So you have -5 minus -1, -4. The non-leading diagonal elements remain unchanged, and you have -2 minus -1, which is -1, times my x0 y0, and I equate it to 0 0 because it is a 0 vector. We are in the order of our main matrix is 2 by 2, so that is why we have the 0 vector of this form. So from there we can multiply and we have a system. -4 times x0 is -4x0, 2 times y0, 2y0, so you add the 2 and you equate to its corresponding entry 0. Next, 2 times x0 is 2x0, -1 times y0 is -y0, and equate to its corresponding entry, which is 0. So we can try to simplify. We see that if for the first equation we divide throughout by -2, we are going to get 2x0 minus y0 to be equal to 0. The second equation remains intact. So these two equations boil down to one equation because they are the same. It's a system. So the first and the second is still the first, or it is still the second. So we have 2x0 minus y0 to be equal to 0, meaning that our y0 is equal to 2x0. Now, having y0 to be equal to 2x0, we can now write our u0 vector as x0 y0 to be equal to, in the place of x0 I maintain, but in the place of y0 I put 2x0. So from there we can factor out x0 from the matrix and we get x0 times 1 1. It means that our eigenvector u0 is going to be a span of vectors. So it is going to be the span of all these vectors because x0 here is a constant. So for simplicity, I'm going to let x0 to be equal to t, where t is a real number, and from there I'm going to get my u0 vector to be equal to the span, that is the set of vectors t into 1 1 2, where t is a real number. So when t is 1, I have the first, when t is 2. So there are infinite number of eigenvectors associated with lambda equal to -1. So the eigenvector associated with lambda equal to -1 is the span of all these vectors. Alright, so let's get now to lambda equal to -6. I named it lambda 1 and its eigenvector is u1. That is, u1 is equal to this column this vector represented in the column form by the mathematical definition of the eigenvector associated the eigenvector associated with the eigenvalue lambda 1. We have this definition. Now we just repeat the same process. So our lambda 1 now is -6. To get a minus lambda 1 times I, which is this, we just replace lambda here with lambda 1, which is -6. So this entry becomes -5 minus -6, which is 1. The non-leading diagonal entries remain unchanged, and this other entry becomes -2 minus -6, which is 4. So multiplying the two and equating to 0, 0, we have 1 times x1 plus 2 times y1. You have the first equation. 2 times x1 plus 4 times y1. You have the second equation. Now we see that if we divide the second equation all through by 2, we are going to get exactly the first equation the same. So the 2 boil down to one equation, and from there we can express either x1 and x2, either x1 in terms of y1 or y1 in terms of x1. It all depends on you, but I always hate to deal with fractions, so in this case I am going to express x1 in terms of y1. So from there we get x1 to be -2y1. Now we rewrite our eigenvector, replacing x1 with -2y1 and leaving y1 unchanged. Now factorizing y1 out, we get this. So we can conclude by setting maybe y1 to be another constant beta. Then we can conclude that our eigenvector associated with the eigenvalue -6 is a span of all these vectors, that is beta times the column vector -2, 1, where beta is a real number. So that was that in determining the eigenvalues and the eigenvectors of the matrix A. And for sure, since we have 2 eigenvalues and 2 eigenvectors, then the matrix is diagonalizable, provided maybe you were being asked to determine if the matrix is diagonalizable. So you just need to show that the number of eigenvectors is equal to the number of eigenvalues, and you can proceed by expressing the matrix in the form P D P inverse, where P is the matrix of eigenvectors and D is the matrix of eigenvalues, and you're done. But since the question just asks us to determine the eigenvalues and eigenvectors, I think we can end here. Okay, so let's go to the next part of the exercise 4, which was part 2. Consider the integral I, which is the integral of y squared dx dy in that domain D, and you have been told what D is. It's the domain enclosed by the circle centered at the origin and of radius 2. So we begin with the first part of the equation, which is asking us to represent graphically the domain, that is the domain D. So I would like us to first of all get the analytical expression of this domain D before we graph it. So firstly, we're being told that the domain D is enclosed. That's the first word, enclosed. Now what is it enclosed by? It is enclosed by a circle. Now what are the characteristics of this circle? The circle is centered at the origin, meaning the center of the circle is a point 0, 0, and the radius of the circle is 2. So 3 key things. First, enclosed by a circle. Enclosed by a circle centered at the origin and radius 2 means that the region, that is this D, is a region of space that is inside a circle, because the circle encloses that region D. So this D is set of points that are inside the circle. They can also fall on the circle actually, and the circle is what, centered at the origin, and the radius of the circle is 2. So let's first of all try to plot the circle itself, because this now represents the analytical expression of my domain D, a set of points that is couples x and y in arrow squared. Here is a circle, x minus 0 all squared plus y minus 0 all squared less than or equal to 2 squared is now my D. The less than or equal to, the less than is for the enclosed, meaning that the set of points are inside the circle, and then the equal to, it means that they can also fall on the circle. So let's begin by plotting these points that fall on the circle, that is the circle itself. So our xy plane, now remember to label them x and y, centered at the origin, that is the circle. So we need to find where the circle gets this coordinate axis. At this point, it is getting the x-axis is when y is 0, and getting the y-axis is when x is 0. So when y is 0, we just have x squared to be equal to 4, so x is plus or minus 2. So here is negative 2 and here is positive 2. When y is 0, when x is 0 this time around, y will be equal to 4, meaning y squared will be equal to 4, meaning y is plus or minus 2. So plus 2 here and minus 2 here. So the circle is centered at the origin, that is the point 0, 0. So it is going to get the coordinate axis at those respective points. Now the radius of the circle is also important to indicate. It has a radius of 2. That is the distance from the center of the circle to any point on the circumference. I just choose this point. Though the distance from the center to any of these blue points indicated is still the radius of the circle. Now let's now draw the domain Z, which is the enclosed circle with characteristics as we have seen. So we simply have now this region. This transcripts to telling us that the domain Z is bounded actually. So this entire region inside is my domain Z. So that's the representation of the domain Z graphically. Second, determine the Jacobian associated to change of variable from the xy wall to the arrow theta wall, such that x is equal to arrow cosine of theta and y is equal to arrow the sine of theta. So we want to change from the xy to arrow theta, that is the Jacobian associated to this change. So simply, here is a formula, because I'm changing everything. So changing dx dy to because here is my integral on this domain. I can see dx dy there, so that is actually what I'm taking to. So taking xy, they have given me x, they have given me y, quite alright. But now also I need the x dy to change it to the arrow theta wall. That's what I need to do, and I'm looking for the Jacobian associated. So here is a formula that we need to apply. So we just need the determinant of this matrix here, that's the partial derivatives, the matrix of partial derivatives of x and y with respect to arrow and theta respectively. Alright, so x is equal to arrow cos theta. We need these entries: partial derivative of x with respect to arrow and partial derivative of x with respect to theta. Differentiating x partially with respect to arrow, every function of theta is considered as a constant. With that, we are going to see that the partial derivative of x with respect to arrow is cos theta, because cos theta will be a constant, and differentiating arrow with respect to itself, you get 1. Differentiating x with respect to theta, all functions of arrow are constant, so we have arrow. Now differentiating cos theta, you get negative sine theta. We do the same principle for y. Differentiating y with respect to arrow means all functions of theta are constant, so sine theta is a constant. So the partial derivative of y with respect to arrow is sine theta. Differentiating with respect to theta, all functions of arrow are constants, hence sine theta is what we are differentiating. Doing that, we get cos theta. So from there, we build up our dx dy, that is a determinant of that whole matrix of partial derivatives. To be equivalent to the determinant of this matrix, we just replace the corresponding entries with their values. Now we can find the determinant of a 2 by 2 matrix. So we have arrow cos theta times cos theta, which is this, minus negative arrow sine theta times sine theta. The two negative signs gives us this positive sign, and we get this. Now we can factor out arrow, and we are going to get arrow into cos square theta plus sine square theta. But we know cos square theta plus sine square theta is 1, so at the end we get arrow times 1, which is arrow. Hence my dx dy is turning to arrow, which is the determinant of my matrix of partial derivatives times the arrow, the theta. Alright, thirdly, evaluate using a change of variable, using that change of variable. So my I is this integral. So I begin, my d is the domain that we have. Now my y is what? R sine theta, that is y. My dx dy is r d theta. So I begin by changing them. So I have the integral in this domain. My y squared becomes r squared sine squared theta, which is this, times my dx dy becomes r d theta, since you have gotten it, the Jacobian associated with x and y. Alright, so from here we can write r squared times r is r cubed. So we have integral in this domain of r cubed sine squared theta dr d theta. Now our region D is represented by, analytically, by this inequality. So it is a definite integral because it is on a domain, so we need the bounds. Originally, since it is a double integral, then we have a range of x and we have a range of y, meaning x is from a region from a certain value to another value, and y is from a certain value to another value. But now we are not interested in getting where x and y lie. We are interested in getting where r and theta lie, because now we have changed it to the r and theta wall. So we need to get the bounds of r and we need to get the bounds of theta. So let's consider just this part, which is x squared plus y squared, because this is x squared, this is y squared, less than or equal to 2 squared, which is 4. But we know x as r cos theta and we know y as r sin theta. So fitting in the respective places, we get this. So here becomes r squared cos squared theta plus r squared sin squared theta, which is just r squared, sorry. So we have r squared less than or equal to 4. From there we can have r squared minus 4 less than or equal to 0. You can do a difference of 2 squares here and you get r minus 2 into r plus 2 less than or equal to 0, and you get the solution of, that's the range where r lie. Alternatively, we can take the square root on both sides. From here you get the square root of r squared to be less than or equal to the square root of 4, which is 2. Now from there, the square root of r squared is the absolute value of r, so we get the absolute value of r less than or equal to 2. From there it means r lies between -2 and 2 from the definition of the absolute value of a number less of a variable less than a constant. But we know that r is greater than 0 because it is a length, actually, because r is the length of a point, of any point on the r theta plane. We call it the polar plane. The distance between any point on the polar plane to the origin, that is r. And since it is distance, it means it is positive, so it cannot take negative values. So simply I'm going to cut off this negative part and I'm going to begin r from 0. So it has a minimum value of 0 because it is always greater than 0, and it has a maximum value in this case of positive 2. So our theta is in the interval 0 to 2 pi for sure, because we are spanning, that point in the polar plane is spanning around a circle. As you can see, our domain D here represents a circle, and beginning from 0 it goes and comes back. That's revolved, or it has traveled a distance of 2 pi. Okay, so from there we can get our I to be the integral. Now I fit my bounds. 0 to 2 pi is for theta, 0 to 2 is for r, and then of my integral. Now I try to integrate each separately. So I begin with r because I can easily do it. So I'm going to rewrite this as, I'm going to integrate r cubed with respect to r, and then now at the end I replace the value here, and then now I work it out with theta. Fundamental theorem of calculus. Integrating r cubed, we get r to the fourth on 4. My bounds are 0 and 2. So upper bound going to give me 2 to the fourth on 4. Lower bound is going to give me 0. The 2 to the power 4 is 16, divided by 4 is 4. So we get that. So it means our integral I is simply 4, which is replacing 4 with this here, times the integral from 0 to pi on 2 of sine squared theta d theta. Now we need to integrate sine squared theta d theta. You see now we are just integrating with respect to theta with its respective bounds 0 and 2. So we first of all convert sine square theta to cos 2 theta. That's the easiest way to do it. It is half into 1 minus cos 2 theta. It means I becomes 4 times half into 1 minus cos 2 theta d theta. That is the integral. Now we can try to factor out the half, and we get 4 divided by 2, which is 2. We integrate 1 with respect to theta, we get theta. We integrate cos 2 theta with respect to theta, we get half sine 2 theta. Now my limits of integration 0 and 2 pi. When you fit your upper limit, you get 2 pi. If you fit 2 pi here, everything here gives you 0 because you have the sign of even multiples of pi is 0. So fitting 2 pi for theta, you get 2 pi minus here you get 0. Fitting the lower bound 0 here is going to give us 0 minus 0. So at the end you just get your 2 outside here and times the 2 pi. Hence you get your integral I to be equal to 4 pi. So that's that for the video.